Hi, welcome to a quick review for calculus. This is specifically for my computational methods class, but it should be helpful for any calculus class because I want to go over the basic ideas of derivatives in this video, and then in another video, I'll go over the idea of integrals. But the general idea behind a derivative is that it is the slope of the line that is tangent to some curve. So in this picture here, you see that I've drawn this curve f of x that's in red. And let's say I'm interested to know what the slope is at x equals 2 at this point here that I have in blue. If I were to draw a line that's tangent to the curve, tangent meaning it touches the curve at that one spot, I would learn that the slope of that line is equal to the derivative at that point. Now, derivatives are important because in engineering, things are changing a lot of times. Things change as a function of time or as a function of position or whatever variable you can think of. And that's what a slope is. A slope is a rate of change, which is why we're motivated to understand how a derivative works. Now, I want to just go through a quick definition as how we'd actually find this and conceptually see where this comes from. But let's imagine that instead of dealing with calculus, we go ahead and look at algebra. And maybe a way to estimate the slope at that point, x equals 2, is to pick another point some distance away. Maybe this will be at 3. And I will draw a line that connects the two. This is no longer the tangent line. This is what's known as a secant line. And I want to find the slope of that line. So what we would do is say, okay, the slope of the secant line, if we think back to high school algebra, that is the idea of rise over run, where the rise is the distance in between these points. This is basically our y2 and our y1, so the distance between those, divided by the run, which is the distance between these two. And just for general purposes, I'll just say that this is x2 minus x1. Now, we rarely will use this form of the equation with the y's and the x's. We write it a little bit more in a calculus sense, where if I were to say, okay, instead of 2 and 3, let's just call this point x1 and x2. And I'll say that they're separated by a distance that is h apart. That's our step size is what we'll call that. What we'll say instead is that the slope of the secant line will be y2, which is found if I plug x2 into the function. So basically, y2 is the same as f of x2, because if I plug in x2 into the function, I will get that as my output. So that is y2. I will go ahead and subtract y1, which is the function value evaluated at that x coordinate. So if I plug in x1 into the red curve, that will give me that blue dot. That's the y value at that point. And then I will go ahead and divide by the distance in between the points. Now, in general, looking at this, x1 is what it is, but x2, if I wanted to rewrite it in terms of x1, that would be the same as x1 plus h. So I can say that the slope of the secant line is f of x1 plus h minus f of x1 divided by h. Because again, x2 minus x1, even if you solve this, you see that that's the distance in between the points. And this should look familiar. Maybe you've taken calculus already, and maybe you've recognized that this is some form related to the derivative, but there's one crucial thing that's missing. But I'm hoping at this point we understand that the slope of the secant line is just found by picking two arbitrary points and finding the slope between them, rise over run. And then we will write it in function notation where we include arguments based on the x values that we have. Some x plus h and then some x. Now this slope will become more accurate as the distance h decreases. So if I were to say, okay, let's do a new h, I'll do it in green. Let's say that this is our new h away. So now I'm only between here. And I were to draw a line connecting those two. Oops, I'll try to make that a little bit more realistic. Yeah, fine, good enough. Now I have a slope that's starting to look more like the slope at that point. And then if I make h even smaller, let's go ahead and do maybe orange. Let's say I make this the point of my h. So now h is even smaller. And if I were to draw a line that connects those two, now I'm getting something that looks more like the derivative or the slope of the tangent line. And basically, the only difference between these two is to say that the slope of the tangent line is the limit as h approaches 0 of that expression. And I'll do it just in terms of general x. It doesn't need to be some x1 that's kind of arbitrary and related to the problem that I wrote. But this is the definition of the slope of a tangent line, which is the same as our derivative, which I will say is f prime of x. That is our conceptual review of what's going on. All I'm looking at is what is the limit as h goes to 0. Basically, as this orange point moves closer and closer and closer, eventually you will be able to determine what the slope of the line is at the point of interest, some arbitrary x1, for example. And we can expand upon this. We're not going to do any proofs of this, but what's nice is that depending on the function at hand, there are certain rules that allow us to find derivatives very easily. Let's just look at some classic rules for differentiation. But the first one being the power rule, where if I give you some function f of x is equal to x, let's say, squared, if I were to take the derivative of this, we know that we take the exponent down and then subtract 1 from the exponent, which is just x to the 1. If I give you something like 3x to the 4th, that exponent comes down. We multiply that by the 3, and then we subtract 1 from the exponent. You get 12x cubed. That should be fairly easy. The next one that's important, let's say, is the product rule, where if I have two functions multiplied together, let's say I have some f of x times some g of x, the derivative of this will be the derivative of the first times the second plus the derivative of the second times the first. So as an example, let's say I tell you that we have a function, I don't know, I'll call it y is equal to x e to the x. Y prime will be the derivative of the first. And if we think about the first and the second, let's say that this guy is f of x and this is g of x. The derivative of the first is 1 times the second, which is going to be e to the x, plus the derivative of the second. The derivative of an exponential is itself. If I just have e to the x, that's just going to end up being e to the x times f of x, which we know is just x. So this will end up being e to the x plus x e to the x. Again, this complicated expression, well, I don't say too complicated, but this expression in general is telling us the slope of that curve at any arbitrary point x. So if I plug in x equals 1, I can see what the slope is going to be at that point at x equals 1. We're not going to worry about the quotient rule, but what I want to explain too, which is more related to the power rule, is the situation where you have, let's say, a fraction. So let's say I tell you that f of x is equal to 1 over x. And I think the best way of handling a situation like this is to go ahead and write the x with some sort of negative exponent. Because remember that negative exponents just flip quantities about the fraction bar. So if I have, let's say, write this as x to the negative 1, what that means is that if I were to make that a positive 1, I have to flip it about the fraction bar. So these are equivalent. And now if I take the derivative, I can do the same exact thing as before. I will multiply by the exponent and then subtract 1 from the exponent. And that is the derivative of that function. The thing that I think trips people up the most is the concept of the chain rule, which we secretly do all the time. We've already done it for these previous problems, but we haven't really been thinking about it like that. Let's go ahead and say that we have some function, f of x is, let's say, 2x plus 1 squared. We see that we have this expression on the inside that has a lot of terms in it. Let's compare this earlier to when I had x squared, that became 2x. Let's try to do that same type of thing. Let's bring the exponent down. Subtract 1 from the exponent. But now what I have to do is also multiply by the derivative of the thing that was inside those parentheses. That is the idea of the chain rule. So the derivative of the inside for this expression here is just a 2, which means that the equation here will be 4 times 2x plus 1. That is the derivative of that expression, which of course I can write as 8x plus 4 if I wanted to. And, if you didn't want to do that, you could write this out as 2x plus 1 times 2x plus 1. You can see that this is going to end up being 4x squared plus 4x plus 1. If you take the derivative of that, you get 8x plus 4. Same exact thing. The reason I say I've been doing this the whole time is that if we look at this expression, I brought down the 2. That's this guy. The inside stays the same, and then I multiply by the derivative of the inside. Well, what's the derivative of x? That's just 1. We're implicitly doing that, or we're automatically doing that by taking that. But when we have some other function that's more complicated than just x inside of parentheses or inside some other function, we have to make sure we take the derivative of that function. So if I were to write it in a definition sense, if I have some function f where inside of f is another function g, the derivative is going to be the derivative of that whole thing times the derivative of the inside. So comparing to this, in our example, this is our g of x, and our f of x is that quantity squared. So I take the derivative of f, so I bring down the 2, and then I have to multiply by the derivative of the inside, which brings out the extra factor of 2. That is the 2x plus 1 expression from there. Let's prove this in a different way. Let's just say that I give you f of x is 4x squared. We know the derivative. That derivative is 8x. We will keep that handy for us to confirm our work. Let's write this, though, a little bit differently to say that this is 2x squared. If we were to do the chain rule, first I will take the derivative of the whole thing, which will bring down this 2. And the exponent on that subtracts by 1, so now we have a 1 there. And then we multiply by the derivative of the inside. The derivative of this is just 2. This gives us 8x, exactly the same as what it was when we just did it the normal way with the power rule, just to give a different idea of things. Other important derivatives are natural log. So if I give you f of x is the natural log of x, the derivative of that is 1 over x. Again, multiplying by the derivative of the inside is 1. If I were to do ln of, let's say, x squared, the derivative of this is 1 over the inside times the derivative of the inside part. So the derivative of this argument here, of this guy, is going to be 2x. This ends up being 2 over x. We can get more complicated with sines and cosines. The derivative of sine is cosine. If we kept going, let's say I take the second derivative, that will give us negative sine of x. Go again. Negative cosine of x. And then if I do the fourth derivative, that'll just start the sequence over again. And a problem that I gave in class, at least to my summer 2025 semester, just as a first day, see how you're doing, is let's say I give you the function f of x is sine squared of 3x. We have a lot of chain rule stuff going on, and let's see if we can understand what's happening here. If you look at this squared, and I'll write this in a sense that to make sure we're on the same page. Maybe I'll try to do different colors. Sine. I'll do it in red. Sine of 3x squared. So just like before, we'll bring the 2 down, and the inside will stay the same. So the inside, let me change my colors a bit so I can be clearer. Leave the black there. That's better. The inside is going to be exactly the same. Like that. I brought the 2 down, and now I am done with that first part of it. Now I need to multiply by the derivative of the inside. Well, the derivative of sine of 3x, or rather just the derivative of sine, is cosine. So I'm going to multiply this by cosine. And I'm going to do it in black, actually. Cosine of 3x. That handles our red portion, our red function. And then we have to go one more time because the sine also has a function inside of it. The derivative of 3x is 3. This ends up being 6 sine of 3x cosine of 3x. So depending on how complicated the function is, it might make life a little annoying. But if we focus on the idea of product rule, chain rule, power rule, we can leverage a lot and we can solve a lot of problems. So just to recap, derivative is the slope of the tangent line. It is approximated, not exact, by the secant line, where you have 2 points that are some distance h apart. And as the distance h gets closer and closer and smaller, we end up taking the limit as that h goes to 0, and that will ultimately give us the exact slope of the tangent line, which is the derivative. And we skipped all the steps that you do in Calc 1, where you'd plug in things into this and see what f of x plus h is and take the limit. We're skipping that. We're just going to the rules that you should already be familiar with. This is a review. So we can see we have a power rule, where again, we take down the exponent and then subtract 1 from the exponent. We have our product rule. We're going to multiply the derivative of one function by the other and then add. If we have fractions, I think that that's easiest to make the exponents negative. And then lastly, the chain rule, which is probably the hardest one that people typically forget. The idea of if you have a function within a function, you have to make sure you take the derivative of the outer function and also the inner function. If you have questions, please let me know. Hopefully this was a decent review. Please comment or message me if you have any further questions. Thanks, guys.